Okay, hi everybody. There's still a few people joining, but I'll do my intro bit because that's not really very interesting to everybody anyway, and then we can get started. So welcome to the next of the RSE webinar series. Today we have David, who's going to give us an introduction to Meltdown in terms that probably people can actually understand rather than chip designers can understand. David has headed up the training at EPCC for quite a long time now, and has a large amount of experience with HPC and trying to explain some of the more complicated concepts in terms that mere mortals such as myself can understand. So without further ado, I think I'll hand over to David and he can get us started on the presentation.
Hopefully you should be able to hear me and see my first slide. So is that going okay, Andy? Fine. So this talk was really written as a try and explain what the issues around the Meltdown vulnerability were. But actually, I think it's actually most interesting because it illustrates quite a lot about how modern hardware and operating systems work, which is hopefully interesting. So even if you're not interested in the Meltdown vulnerability in itself, hopefully this will sort of get you thinking about how things actually work under the hood. And the reason for the logo soup on the front page is this talk was originally given as part of the Archer webinar series, maybe 6 months to a year ago. I can't remember exactly when. So I've called this The Road to Hell is Full of Good Intentions because I think, you know, we can reuse this material if you want in the normal way, because I think a lot of the decisions which were taken which led to this vulnerability were actually very sensible and well-intentioned. It's just at the end of the day, added together, they led to this vulnerability, which I'm going to describe. And it was actually St. Bernard of Clairvaux, not clairvoyant, but Clairvaux, who a long time ago, I think it was 14th, 15th century, said, the road to hell is full of good intentions. And so, you know, we start off with our computer, and through this Meltdown vulnerability, we end up in, well, what you might call computer hell. But so maybe we should have listened to St. Bernard of Clairvaux. But well, as I said, what I hope to do in this talk is show you that all the components that lead to this vulnerabilities are very sensible and well-intentioned and beneficial to users in themselves, but also the interaction of these things with the way that hardware and system software works leads to a quite unexpected way of accessing data you're not supposed to be able to access. So I'll go through with an introduction. Most of I've got the whole talk here, but I actually will basically only do the introductory analogy and then the summary here. I'm not going to talk about the anti-meltdown patches and the performance implications because they were only really relevant for the Archer talk. But I've left slides here just for completeness, but I'll kind of skip them because I need to leave 1:45. So I have about, hopefully I won't talk much beyond 25:2 and give us 10 minutes for questions. So, I mean, this slide is new from the last time. I mean, there was an enormous amount of interest in Meltdown. If you look at the number of Google searches for Meltdown, you know, basically early in the year, you can see the huge spike. We took it quite over the first month, and there was a lot of interest, and it seems to have died down now. This talk is at a very conceptual level, but there is a talk online that I found from Professor Mark Handley of UCL. He gave a talk at the Alan Turing Institute, and I've given the link there, and that gives you a lot more of the technical details. So my hope was that this talk is really, in some sense, an introduction to that talk, so that you have some conceptual model for what is spoken about there as to how it all fits together. So clearly there's a lot of interest in Meltdown. What was Meltdown? Well, if you look on Wikipedia, it says Meltdown exploits a race condition inherent in the design of many modern CPUs that occurs between memory access and privilege checking during instruction processing. Combined with this cache side channel attack, this allows a process to bypass the normal privilege checks that isolate the exploit process from accessing data. The vulnerability allows an unauthorized process to read data from any address that is mapped to the current process's memory space. So hopefully I'm going to explain all these highlighted terms here in common or garden language. But I think just to really summarize, the major issue with the Meltdown vulnerability was it allowed any user on almost any modern system to read any memory. So basically, you could log on to a system and read the memory of that whole system, any process, any other user's memory, including their passwords, any sensitive data, their email, anything. And the whole point about modern operating systems is they're supposed to exploit, they're supposed to isolate users from each other. That's what you always assume. But this exploit allows you to read the memory, the entire system memory, including all the data in everyone else's processes, containing everything on the computer, clearly sensitive data. So what I'm going to do is I'm going to try and explain how it worked, but using an analogy. So I mean, a bugbear of mine is that, you know, computers are analogies. So when I was going to give this talk, I thought surely there's an everyday situation that exhibits the same behavior, because I've got some pictures here, but you know, the fact that you have keyboards as an analogy to what typewriters were like, the fact that we talk about files and folders and directories as an analogy to physical filing cabinets, the fact we use desktops, which with Windows that we move around, is an analogy to a physical desktop with garbage and papers lying around. So computers are built to be analogies. They're built to mimic, you know, what we do in everyday life. And so the analogy I came up with was that the machine is like a lawyer's office. So that's what we're going to talk about. We're going to a lawyer's office. The operating system is the lawyer, and the memory system is the legal clerk. The RAM are filing cabinets, and the accessible data are my legal documents, and the secret data are other people's documents. So basically, we've got a situation where I've got somebody, a lawyer, who stores my legal documents, but I'm going to find out a way to access other people's documents, stuff I shouldn't see. And I think that this analogy hopefully illustrates how the meltdown vulnerability works in practice. So here's a diagram to kind of explain who the actors are. So here's the lawyer's office. Here am I. I'm in the front office, and I'm represented by, and this is the back office here, which I can't see it. There's kind of a wall here, and I'm represented by this sort of naive simpleton here, for obvious reasons. And I'm speaking to a lawyer, and she is going to deal with my transaction. And in the back office, I have my file. So I've lodged sensitive documents with the legal office, but they also have things, secret files I'm not supposed to see. So I turn up at the front office, and I'm going to have to try and trick the lawyer into giving me access to sensitive information, which I'm not supposed to see. I'm going to trick the lawyer into giving me access to these secret files when I should only have access to my files. That's the setup. The analogy to compute, and there's a clerk who does all the back office stuff. The analogies, I think, the computer equivalents aren't exactly perfect, but in my mind, the analogies work like this. In the front of house stuff is software. The back of house stuff is hardware. I'm a user program, and the lawyer is sort of the operating system. So I interact, my interaction with the hardware, with the back office, is via the lawyer, and she's just sort of behaving like the operating system there. And this is user memory, which is my memory. My user program has my memories. This is the memory I'm supposed to see. And this is operating system kernel memory. This is secret stuff the operating system stores. It's in a safe. I should not be allowed to see it. And the memory system, the clerk, operates like the memory system. And basically, the vulnerability comes about because modern memory systems are very, very complicated and sophisticated. And it's actually that which leads to this exploit. So I'm going to go through a few simple things first. So a memory request. So I want to access my own memory, the memory in my process. So what I do is I come in, and the analogy is I say to the lawyer, can I see document number 1, please? So in the back office, I have document 1 here. And what she does is first of all, she checks I'm allowed to see it. So she says, can I see your ID? So I give her some ID, and she says, okay, that's fine. I believe who you are. You're allowed to access this memory. But the way that modern computers work is the operating system doesn't really directly access the memory. It asks the memory system to deliver out memory. And here the memory system is a little lackey called Igor. So the lawyer gets Igor to go, and Igor goes off, gets document 1. And this is taking a long time, but okay, gets document 1, brings it back, gives it to me, and I can read it. Okay, and that's all fine. So just to go back, that's a normal request. I say, can I see my document number 1? There's a check to check I'm allowed to do that. I give my documentation, my identification. The lawyer says that's okay. She asks the memory system to get that data. The memory system goes away. This takes quite a lot of time, but it comes back with the document and delivers it to me, and I can read it, and then goes back and returns it to the system. How does an illegal request work? It's very simple. I say, can I see the contents of safe number 0, please? Clearly, safe number 0 is something I'm not supposed to see. I'm asked for my ID. I provide my ID, and of course the lawyer says, well, no, you're not authorized to see that data. Okay, and I say, I'm told to go away, and I apologize for what I've just done. So that's the way that memory systems work. That when you ask to access some memory, the operating system checks, is the process asking to access memory which belongs to the process? If not, then it says no. Seems quite straightforward. So the good intention, so GI number, good intention number 1, the office should operate quickly. So it would be really, really slow to go to a different office every time the client wanted to access the secret documents. So you may have noticed in this diagram that the secret documents were stored in the same back office as my documents. So that's not immediately, you might think that's a bit of a strange thing to do. Why aren't the secret documents stored in some off-site location? The problem is, it would be really slow if every time we wanted to access one of the secret documents, the memory system or Igor has to go to a different office. So what we do is we store all the information, both secret and non-secret documents, in the same office. And we basically just deny access if people aren't authorized. And the way that happens in a computer is when you launch a program, actually you are allowed to see the entirety of the RAM of the computer. The entirety of the computer memory is mapped into the virtual address space of all user programs. So you can access all user memory, so all physical memory. What happens is the operating system checks the privileges of the accessing process and says, no, you can't do that. Only kernel processes, only privileged processes are allowed to access privileged memory. We've already made a design decision to store all the memory in the same place. We could have just said, look, user processes can't even ask for a privileged memory, but that would mean it would be slow whenever the lawyer wanted to access the documents which she's allowed to see. So we've stored them all in the same office, and that's the first element of the vulnerability. In principle, all memory is accessible to every process, but the operating system just says no when you're not allowed to see it. So now, from now on, we'll assume that all accesses are valid just for ease of operation. So the unintended consequence of that is that I can see the secret documents, so I can ask them. I'm in the office, there's some secret documents there, I can ask them. If we stored them somewhere else in a different office, I wouldn't even know they existed. So that's the analogy I'm going to use here. So what actually happens, so let's go on memory request, can I see my document number 1, please? And the lawyer gets Igor to go away, get document number 1, and Igor delivers the document and then goes back. I say thanks, and Igor returns it back to where it came from. But I realize I want to see that document again. So I ask for the document again. Can I see it again, please? And off Igor goes, has to get the document, has to come back, has to deliver it, and then go back, and all the way back again. And just to really cheese him off, I decide I want to see it again. And so Igor has to go again, get the document again, bring it all the way back, give it to me, take it all the way back, and he's done. So we're achieving the right thing. I'm seeing the document, but Igor's a bit upset. He doesn't think he's being paid enough to do all this running around. And so, this is very, very slow. And we know that in computer programs, you tend to ask for the same memory many, many times. You read a value, you read it again, you read it again, you read arrays, variables very often. So what's the way around this? Well, Igor has a bright idea, and he buys himself a table. Now, the table is in the back office. It's a small table, but it's enough storage to store a couple of documents. So in the back office, behind the scenes, which we can't see, Igor has made a little optimization. He's bought himself a little table. So what happens now? Can I see my document number 1, please? Off Igor goes. Igor goes and gets the document, brings it back, delivers it to me. But he doesn't store it back in the memory system. He actually sticks it on the table. He thinks, I think that this user is going to ask for this memory again. So he sticks it on this little table and then goes back to where he came from. So when I ask for the memory again, can I see my document number 1 again, please? Igor, it's much quicker, okay? Igor just goes to the table, picks up the data and delivers it to me. And I notice that was quick. So, there is sort of, so behind the scenes, there's this table, which is behind the scenes. So I don't know what's happening, but I can infer that Igor is doing something clever because the second time and subsequent times I ask the document, it comes back quickly. So, and on the way back, he stores it back on his table. And he's happy now. So the good intention too is that memory access should be fast. Why keep going back to document store all the time? Keep recent documents close at hand, but still secure in the back office. And this is the analogy that modern computers where access to main memory is cripplingly slow. Memory systems keep copies of recent data in fast cache memory. So reads and writes apply to the cached copy. It's done automatically in hardware. You don't see this. You just say, can I read X, please? Can I read Y, please? You just access memory. But you can tell it's being cached because it might come back quickly. Okay, so this is there deliberately to make programs quick. If a program reads the same memory lots of times, you don't go all the way back to the slow memory. There's a little copy stored in the cache, which is accessible to you much more quickly. So functionally, you get the same outcome. You can read and also write data, but it goes faster than it used to do. But this does have some unintended consequences. So on the bus home, I saw my partner, and my partner's car was at the lawyer's office. So I say to them when I get home, we're having our tea, I say, having our supper, I say, oh, I saw you at the lawyer's office today. Oh, yes, I was just checking the mortgage arrangements. Okay, that's fine. But I'm a bit suspicious. So I go into the lawyer's office and I say, can I see our mortgage arrangement? And she says, I'll have Igor fetch it for you. Oops, sorry. And we wait, and we wait, and we wait. And eventually the document comes back. That took a very long time. Now I'm suspicious. I think, well, if my partner had actually been looking at the mortgage arrangement, it would have been stored in Igor's little table. So that would have been quick. So I now have access to information I shouldn't really have known. Although my partner said that they were looking at the mortgage arrangement, I know they weren't. So I get a bit suspicious. I'll say, okay, could I see our prenup agreement, please, which is also stored in the back office? Igor goes, oh, it comes back really quickly. That was very quick. Now I'm suspicious. My partner was looking at our prenup agreement on the way home and not at the mortgage arrangement, as they said. So that's actually a bit worrying. So the unintended consequence is that accessing documents that I'm allowed to read can give me information that I'm not allowed to have through differences in timing. Okay, so I was allowed to read that document, but I wasn't allowed to know if my partner had been reading it. But because of differences in timing, because it came back quickly, I know that somebody else had been reading that document, and therefore it must be my partner. And so on a computer, the time taken to load data from memory tells you if it was cached. You can deduce whether or not it has recently been accessed. Okay, so that's the second point. Now let's return to the authorization step. So authorization, we skipped that in the past few slides. So I come in and I say, can I see my document number 1? And the lawyer asks for my ID. I show it to her. And then she has to go and check. She probably has to phone a head office or something to check that I'm actually allowed to see this documentation. So she has to phone head office. So she sits there phoning head office, which takes quite a long time. Then she says, okay, that's all right. She asks Igor to go and get the data. He comes. He gives it to me. He goes back and he stores it on the table because, as we said, we're going to cache these recent accesses for later recovery. So good intention number 3 is authorization should be fast. So why wait to tell Igor to go for the document? Okay. Why don't we just ask for the document at the same time as checking the authorization? So what we'll do is that rather than doing the authorization first and then getting Igor to get the document, the lawyer will say to Igor, go and get the document, at the same time check the authorization. But if I'm not authorized, just don't deliver the document to me, okay? Don't deliver the document until authorization is confirmed. And on a computer, the analogy is that a modern processor in hardware, executes instructions out of order. It doesn't wait for instruction number 1 to complete before issuing instruction number 2. And this is absolutely essential to the technique to keep modern CPUs busy. It's due to the fact that modern CPUs are heavily pipelined. So you only deliver the data to the user program once all checks are passed. And if the check isn't passed, you roll back. You say basically, okay, I'll optimize for the usual case where everything is okay. So normally and we'll deliver the data to the user. But every now and again, if the user has made an illegal request, we'll just roll back and not show them the data. That might take a bit more time, but that's the unusual case. So we've optimized for the usual case where everything is okay. So I'll illustrate the usual case here. So this is how out-of-order execution works in this analogy for a legal access. I say, can I see me a document number 1, please? And now what the lawyer does is at the same time, she's checked my authorization and asks Igor for the document. She asks for my ID, I give it to her, and then she does these 2 things at once. She gets Igor to fetch the document, and she says, let me check. So what happens is Igor fetches the document and stores it in the cache. Now, in the previous examples, I showed Igor caching the data on the return leg. This is actually more accurate a reflection of what happens in real life. When you read data from memory, it's cached sort of on the way out before you ever see it. So that's just a slight subtlety there. But she's checking for access at the same time as Igor is getting the data. Then she says it's okay. So she says to Igor, it's okay, Igor, you can deliver the data to the user at the front of house, and that works fine. So off he goes, and we're fine. So that was fine. I saw my data, but I saw it faster than I did before because the authorization and the fetching the data from the memory were done at the same time. How does illegal access work? Well, same thing happens. I say, can I see safe number 0, please? I'm asked for my ID. I present it. At the same time, the lawyer gets Igor to get the data and checks. Now here I've asked for a legal. Now I'm not allowed to see safe 0, but I've asked for it. So Igor has actually gone to safe 0 and retrieved the data because we hadn't done the authorization check yet. Now it turns out I'm not authorized, and I'm told to roll back. So Igor says, okay, I'm not going to give that data out, and I say I'm sorry. But if you look at this situation, the rollback hasn't been complete. There is still a copy of this data, this red document I'm not supposed to see, which came from safe number 0 in the cache. Now I haven't seen it yet, so it looks all okay, but start to worry a bit here. So there's been a digital fingerprint. The rollback is incomplete. The secret data is in the cache, but I can't read it. If I asked to read it, I would be told, no, you can't see it. Maybe I'd be told quicker than before because it's in the cache, but even so, who cares? I'm not allowed to see it. The rollback is incomplete, but the secret data is still in the cache, but I can't read it. So everything's okay? So then you start thinking, do I have seeds of doubt here? So, I mean, this diagram here shows the 3 the 2 basic concepts which are coming about. First of all is that data is cached. So the data here is cached on this table in the back of, oops, sorry, I'm messing up with my, is cached here. But also we have this out of order execution, which in this example means that my ID is checked at the same time as the data is retrieved. Okay, so those are the 2 components that have come through. So the rollback is incomplete, but I can't read it. Now, here's the final piece of the jigsaw. Many programs have constructions akin to this. You loop over some index, do I equals 1 to n, and you're accessing some array x, xi equals xi, but you're not doing xi equals xi plus yi. You've got some indirection. So what you're saying is I'm not adding yi to xi, I've got some lookup table. So I loop over I equals 1 to n. The index in y comes from a lookup table, and I say xi xi plus y index, okay? So this is such a common construct in modern computer programs that the CPUs have machine code instructions to do this. So you can actually say to the hardware, don't load the data from location I, but load the data stored from location stored in location I. So if I want to read this value y index, I'm saying don't read yi, read y where the index comes from another location. Load the data from a location stored in some location I. And this is the final piece of the puzzle. This is how I can trick the lawyer into giving me information I shouldn't know. So what I do is I don't ask the lawyer for one of my own documents. And I don't directly ask the lawyer for one of the secret documents. What I say is, can I see my document number the same as contents of safe number 0 here? So what I'm saying is, say, go to safe number 0, get at the document. That document set has a number on it. I'm saying, don't tell me that number, but go and get the document which has that number from my file. So maybe more obvious now if I should play out the example. Can I see my document numbered the same as contents of safe number 0, please? So the lawyer says, can I see your ID? Here it is. So at the same time as checking my ID, she gets Igor to do it. So Igor first goes to safe 0, which I'm not allowed to see. He's allowed to see. He opens up, and that document has secret data 3 on it. So I'm not allowed to see that data. I'm not allowed to know that secret document has the number 3 on it. But what I've asked Igor to do is not to give me that data, but to go and give my own document here numbered 3. So I've asked to say, can I see my document numbered the same as contents of safe number 0, please? I'm saying, he then has to say, okay. He then goes back, goes to document number 3, brings it, caches it on the table, but now the authorization comes through, and the lawyer says, roll back. You weren't allowed to open safe 0. Okay, so that is rolled back. So I didn't see that document. Okay, but I did something slightly contrived. I asked to see the contents of document 3, not directly. I said, go to the safe, look at the document in there, look at the number on that document, and give me my document with that number on it. Give me my document number 3. So my document number 3 is cached here, okay, on this table. So we wanted to achieve a way of being allowed to read data we should not have access to. What we actually achieved was a way of not being allowed to read data we do have access to. If I'd asked directly for the contents of my document number 3, I'd have got it. Because I did it by this indirection, because I said, look at what's in the safe, look at the number on that document, it's a 3, go and get my document number 3. But there are side effects. I was not able to read the value 3 from the safe, but my document number 3 is in the cache. And that's the critical thing. I can now say the unintended consequence is that the side effects of indirection are the rollback is incomplete. There's a digital fingerprint in the cache. Produces a side effect of accessing a secret document. I wasn't able to read the secret document, but now I can try and read my own documents and see how quickly they come back. So if we just go back to this diagram here, as we said, I said, can I see my document number the same as contents of safe number 0, please? We did the check. Igor went off. He found that secret document had the 3 on it. I'm not allowed to know that has a 3 on it, but based on the information, he went and got my document number 3. I was not allowed access to that document because along that path there was an illegal access to the safe. So I'm not allowed to see it. We roll back and I apologize. However, what I can do now is I can say, I come back and say, okay, can I see document number 0, please? Have Igor fetch it for you? That took a very long time. You can see where this is going. Can I have see my document number 1, please? I'll have Igor fetch it for you. It's a long time. Can I see my document number 2, please? Get Igor to fetch it for me. Takes a long time. But then I say, can I see my document number 3, please? It comes back quickly. Bingo. So because accessing my document number 3 was quick, I know it must have been in the cache, which means I know that the secret data I wasn't supposed to read in the safe contained the number 3. So that's how so the computer equivalent is what you do in Meltdown in a nutshell. You try to read. I don't go through the details here. I think the talk goes. But you create a big array, which is a bit like that array of documents, and you say you try and read that array, but you read an element based on an index taken from the value of secret data. Okay. The read will fail because you weren't allowed to access that secret data, but the array element will be cached. So I asked to access some memory I'm not supposed to access. If it was a 5, it will then access my array element 5. Then it won't give it back to me. It'll say you weren't allowed to see that. Then I scan through the array element by element. I measure the time taken to read each element to see if it was cached. And if reading element I is fast, then the secret value is I. It's completely analogous to what happened in my office analogy there. And if you look at the papers and such like, you'll find that this allows you to read computer memory at hundreds of megabytes a second. Through this exploit, any user can read, can basically dump the entirety of the system memory and read it at rates of hundreds of megabytes a second. Now, there are some subtleties here, which I won't go through as to how it's done it fast. I won't say how it's done fast. There are some technicalities which I'm not going to talk about here. But here we go through Meltdown exploits a race condition, which is the race condition is a race condition is doing two things at once which conflict with each other. The conflict here is I tried to do the authorization and the access at the same time. Because of out of order execution, I didn't wait for the authorization step to complete before I did the access. I relied on rollback. And as we saw, the rollback is incomplete because there's a digital fingerprint left in the cache. Design of many modern CPUs is out of order execution. The memory access is hardware, but it's the cache done in memory access which allow this exploit. The privilege checking is done by the operating system. And this cache side channel attack was the time taken to read data from the array. And so the reason why Meltdown came about is that there's this separation of concerns where the operating system just says, I want to read some memory, but the hardware does that, but it does it in a very complicated way. And people hadn't realized that the complicated way it was done in hardware had side effects where data which you weren't allowed to read could be, the values of that could be inferred by what was left in the cache. And although you can't read a cache memory that you're not supposed to access, it was the time taken to read that memory which gave you the secret information. Just like when I went to the lawyer and I said, can I see our mortgage statement? Can I see our prenup? Because the prenup came back quickly, I knew my partner had been looking at the prenup and not the mortgage statement. And you can do it from any address that is mapped to the current process's memory space. And again, for speed reasons, all of RAM, the entirety of physical memory, is mapped into every processor's memory space. That's the same as saying at the lawyer's office, they decided to store the secret documents and the public documents in the same back office because to make things quicker. And so there are some slides here as to how it's mitigated, and I won't go through that. And some performance issues. Again, I'll leave these up here for later. Summary, I want to jump to the summary here for matters of time. The summary, at its core, Meltdown is remarkably simple. And I think, in my mind, it's completely analogous to this everyday office situation. That in this everyday office setup, you can read the values of secret documents by indirection and then checking what value is cached. So for many years, both CPU design and operating system design focused on speed. CPUs had caches to make data access fast. Operating systems mapped all of the physical memory into every process just to make things quick. But as we know, speed kills. And so that's my of how the Meltdown bug works. Hopefully, if it's been clear enough, and some acknowledgements here, that will then give you some model, some everyday model, so that when you go and if you want to follow this up, then you can look at that talk given by I can't remember the guy's name. I gave the link at the start where he goes through much more detailed things about how the hardware. So. Do you have to clean the cache every now and again? So someone has asked. So you can flush the cache. You can flush the cache, but you can mark the cache as invalid. But the problem is that I mean basically you have to use caches because you have to use caches because otherwise. Everything would run really slow. What you're saying is, after an illegal access, could you flush the cache? I guess you could. The problem is the hardware never knows it was an illegal access. Okay, the hardware, the memory system just does what it was told to do. So I guess you could do that. You could do that. It might take a while though. I don't know. That's a good question. So currently, the mitigations which I haven't talked about are basically that the patches which you apply to your operating system were to make sure that the operating system memory, the kernel memory, and the user memory were kept in different offices. So you couldn't do this. You weren't even allowed to ask for it. Well, so yeah. So I think that's a very good question. Could the operating system not flush the cache or mark it as illegal? I think Andy's right. If you do it too many times, the performance hit could be harsh. Could you do it on every illegal access? That's a good question. I don't know about that. So what you would say, yes, in that analogy, that Igor would not cache the data if it was illegal. And you would be, that's interesting. Maybe something I can ask that question. Somebody who know the answer. Actually, that's a good question. Actually, it's a good question. So I'm taking questions now. Sorry, I should have. Does anyone have any questions at all, or things that weren't clear about that? I think it's quite important to note that as a user, or even if you're writing assembly language, which is probably the lowest level program you can imagine writing as a user, you do not have any explicit control over the cache. You just ask for data from memory, and it will be cached by the memory system if it wants to or not. You don't say load data from cache, load data into cache. You just ask for variables from memory, and it's cached behind the scenes. Now, presumably, the way to mitigate this exploit is in later revisions of operating system and hardware. There may be instructions, privileged instructions, that allow you to have more explicit control over the cache. I don't know. Validated cache line. Actually, I think I can think why you can't. So what you'd have to do is you'd have to, yeah, okay, I think I know why you can't do what you suggested, because what you're saying is if you see that data has been, you invalidate the data from the cache, but by the time you get around to invalidating it, it may contain some different data. It may have been overwritten by other data, because there are multiple processes, there's only one table, but there's potentially lots of people coming to the office. So I think there is a subtlety there. In the single user example I've given, I'm kind of thinking on my feet here, what you've said, Eduardo said, would be a potential solution. But I think in a multi-user environment, it will be problematic, because the same cache is used for all processes. Physical cache. I need to think about that. So I finished a little earlier, so I do have, if anyone has any questions at all about any other things that I skipped over or any things that weren't clear. I mean, the thing I would say here is that from an HPC side of things, the Meltdown vulnerability isn't that big a deal, because it only works, it's only useful if you have multiple users on the same computer, So for an HPC system like Archer, the login node, I don't know if the patches were applied there, but let's say a generic HPC system, the login nodes are shared between people. So you would want to mitigate against the Meltdown vulnerability on the login node. However, on machines like Archer and other high-end HPC systems, we only access single nodes. We only allow one user to use a compute node at one time. So the Meltdown vulnerability would allow you to read all the information on the compute node, but it's just your data because you're the only user on it. So in some sense, it's kind of a very complicated way of reading data you could have read anywhere. So this really has big implications for shared computing, which is, of course, most servers are shared nowadays. So Andy says, even if nodes are not shared, the file systems are. Does this provide an avenue for exploit even with exclusive nodes? That's a good point. There may be, the operating system may have cached data from another user process. So yes, actually, that's a possible issue. That's a good point. I hadn't thought about that. I don't quite know how much that's flushed though. Don't know. So, as I said, I have to leave in a couple minutes. But there are no questions. Thanks everyone for attending. The slides will be available as PDF, but given there's so many animations in this, which I struggle to get working, I have to say, the PDF might not be that useful. But this has been recorded, so the audio and the video will be online, so you will be able to replay this if you're interested. But the intermediate slides will be available. I thought I'd leave them all in so you can see them in the PDF. So I'd like to thank everyone for attending. Apologies, I have to leave a bit quickly, but I hope you found that useful.
So, thank you, David, and thanks everybody for coming along. The other thing I'd like to say is if anybody who's attending has any ideas or wants to present a webinar or some work they've been doing or something of interest to them, then please just get in touch. We're always open to suggestions for webinars, or even if you want to finger somebody who you know might give a good webinar, feel free to suggest them and we're happy to talk to them and try and set that for people.